What's up guys, and welcome back to this video on projectile motion in one direction. Okay, so we started off in the last video discussing equations of motion, the importance of direction, and we discussed objects being dropped. In this video we are back and we did an example and drew a couple graphs, but we're back to some theory before we get into questions. So let's get back to my black color pen. Okay, so the second scenario or case that we're going to study are objects thrown up and returning to the same position. Okay, so an example of this, probably the most common, and you'll get lots of questions on these, is basically you throw a tennis ball upwards and you catch it back where you threw it from, and yeah, so we discussed that. Okay, so there's some things to note. Okay, so let's actually go with that tennis ball idea. Okay, so let's say I am standing and I have a tennis ball, and then I throw it upwards, right? So it goes up, 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 up. It reaches a maximum point somewhere here, and then comes all the way. Let's do it like this. Okay, so it goes up, reaches a maximum point, and then returns back to the original position. So let's say this is position 1. This is position 2, and this is position 3. Okay, so what can we say about all these positions? Okay, so at its maximum height, so this is the maximum height, right? This position right here is our maximum height. Okay, so at the maximum height, the ball stops going upwards and starts going downwards, right? So that means that at this height, the ball has a velocity. At the maximum height, we can say that the velocity equals 0 meters per second. Okay, so it stops essentially. Okay, then we can also say throughout the entire journey from 1 to 3, from 1 all the way to 3, the acceleration is a constant and is equal to g, right, which is equal to 9.8 meters per second squared, and it's always acting in the downwards direction. Okay, then let's add 2 more points. Let's say we have some point, what's 1, 2, 3, 4, okay, and 5, and these points are at the same place. Okay, so 5, they're at the same position. So the velocity at 4 is equal to the velocity at 5. So at the same height, the objects have the same velocity but different directions. Okay, so at 4 the velocity is the same as 5, but at 4 we're going upwards, and at 5 we're going downwards. Okay, the same can be said, velocity of 1 is equal to the velocity at 3. So it returns back to the person's hand at the same speed that they threw the ball. Okay, and the last thing that we can say is that the time upwards, so the time up is equal to the time downwards. Okay, so basically what I'm saying is the time from 1 to 2 is equal to the time from 2 to 3. Okay, and finally at this point right here, displacement equals 0, right? So the blue shows your maximum displacement, and at the red you have the 0 displacement point. Okay, then, okay, so when we're dealing with this kind of motion, you can also deal with it in different sections. So for example, I can deal with section 1 to 4, or I can deal from 1 to 3, or I can deal from 1 to 5, or 1 to 2, or 2 to 5, or 5 to 3. I can do it in any I can create UVATs for any position, basically, any 2 points. Okay, so with that said, we can go into an example, I think. Yeah, so I did examples in purple. Okay, so this is going to be example 2. Okay, so so an alien on an unknown planet, throws a 3-kilogram ball vertically upwards with a speed of, let's say, 35 meters per second. The alien then catches the ball. Let's say, let's say 7 seconds later, at the same point of release. Okay, so that's the bigger question, and then we will get into sub-questions. So that's just the background to the question. Okay, so the first question A, let's say calculate the gravitational acceleration. Okay, so this isn't on Earth, so we can't just say acceleration is equal to g. Okay, so let's first identify some stuff and maybe even draw a little diagram. Okay, so let's start off by drawing a diagram of the situation. So the alien starts, we have some weird alien, he throws a ball upwards. Okay, and then he catches it back at the bottom. Okay, so our initial is 35. Initial is 35 upwards. It's 3 kilograms and it takes 7 seconds. Okay, I'm going to say that's 1 and that's 2. So from 1 to 2, we take 7 seconds. Okay, I'm going to say this is 0.3. Okay, so from my previous rule, I can break this down and I can say that from 1 to 3 takes half the time, so 3.5 seconds. Okay, so if I wanted to deal just from 1 to 3, I can say it takes 3.5 seconds because the time upwards is the same as the time downwards. Okay, now let's get into some UVATs. Okay, UVATS. Okay, he throws it upwards, so I'm going to take upwards as being positive, and I am going to deal from, so I'm looking, okay, I'm going to deal from 1 to 3, just because I think that'll be the easiest, because I know that the velocity at 3 is equal to 0. Okay, so velocity at 1 is equal to 35. Okay, so my initial is going to be 35. My final is going to be 0. Acceleration is the unknown that I'm looking for. The time is 3.5 seconds. And the displacement is unknown as well, but I don't really care about that. Okay, so now I'm looking, I've got U, V, and T. I'm looking for A. So let's go to my equations. Which equation can I use? I'm looking at equation 2. I've got U, V, and U, V, and T, and I'm looking for A. So that equation works for me. So I'm going to use this equation. Let's see. Okay, so I'm going to say U is equal to V is equal to U plus AT. Okay, so V is going to be equal to 0, U is equal to 35, A is an unknown, and T is 3.5. Okay, so 3.5 A equals minus 35, so pretty simple maths here, guys. So acceleration equals minus 10 meters per second squared. Okay, what does that minus mean? Okay, we took upwards as being positive, so that means the acceleration equals 10 meters per second squared down. Okay, that's just an indication of our direction. Okay, but when I put it into my UVAT, it needs to be minus 10, right? Okay, so question B. Let's keep going. So it says calculate the weight of the ball. Okay, so let's see. Okay, so we know that weight is Fg is equal to mass times gravity. Okay, so the mass was given as 3 kilograms. So we have 3 kilograms times g, which is minus 10. So we're left with minus 30 newtons. Okay, and again, that is just an indication of direction. So we can say this is equal to weight is equal to 30 newtons downwards. Okay, and that is the final answer for that. Okay, okay. Just interpreting question A, the fact that the acceleration came out as a negative makes sense, right? Because it's acting downwards so that the ball goes from going fast to going slow. Okay, so I hope that makes a bit of sense. Okay, so the next question is going to be in purple. So question C. Okay, so will the ball reach a higher, let's say, a higher maximum height on Earth or on the unknown planet? Okay, so basically, we need to do 2 UVATs and calculate this, right? Because we have enough information. So let's start off, let's say we already have the UVATs for the unknown planet. So let's do unknown first. And then we'll compare that to Earth. Okay, so let's get the UVATs, UVATS. Okay, I'm just going to copy them from above. 35.0, 35.0. T was 3,5. S is unknown. Okay, acceleration is minus 10. I'm going to try use an equation that doesn't need acceleration just because that's something I calculated. So if I've made a mistake, then I don't want that carrying over, right? So I'm looking for an equation that does not use acceleration, and I'm looking for S. S is the, or the displacement is the variable that I'm searching for. So I'm looking for something that does not use acceleration. Okay, so the last equation helps me out. S equals u plus v divided by 2 times t. Okay, and again, these UVATs are from 1 to 3, right? So S equals u plus v divided by 2 times t. So I'm left with 35 plus 0 divided by 2 times 3, 5. Okay, so if I do that, I have 35 divided by 2 times 3.5, and we get a height of 61.25 meters. And it came out positive, so I'm going to say up. Okay, so that's for Earth. So I'm going to say that's for, sorry, S of the unknown planet. Okay, so now I want to work out S of Earth. Okay, and the way I'm going to do this, I'm going to write UVATs once again. UVATS. My initial, okay, the initial is going to stay the same at 35. The final is also going to be 0. Acceleration, this time I know what it is. On Earth, it is always a constant and downwards being negative, minus 9.8. The time, this time is unknown. I don't know what the time is, but I also don't know what displacement is, which is what I'm looking for. So I'm going to look for an equation that doesn't use time. Hopefully one exists. So if we look at our equations, okay, an equation that does not use time. Okay, so I'm looking at equation number 3. Okay, so let's go for equation number 3, and we're left with v squared equals u squared plus 2as. Okay, but I'm solving for s, so I'm going to get that as my subject of your formula. So I'm going to say v squared minus u squared over 2a is equal to s. Okay, so s is going to be equal to 0 squared minus 35 squared over 2 times minus 9,8. Okay, and if I plug that into my calculator, the displacement on Earth is 35 squared over 2 times 8. If I plug that in, I get 62.5 meters. And once again, it came out positive, so it's going to be upwards. Okay, so which one is higher? So the displacement on Earth is actually higher. So will the ball reach a higher maximum height on Earth or on the unknown planet? It will reach a maximum height will be greater on Earth. Okay, but that's only marginally. Okay. Okay, Okay, so the next question I'm going to go for is question, what is it? ABCD is going to be, what acceleration would a 50 kilogram ball experience if it is thrown with 4 times the velocity on the unknown planet? Okay, so the question is, what acceleration would be experienced? Okay, so we've been given some information, 50 kilograms, and it's thrown at 4 times the velocity. Okay, but remember that the acceleration on a planet is constant. So the acceleration would be equal to minus 10 meters per second squared, or 10 meters per second squared downwards, because it is independent of so we can say acceleration is independent of mass, okay, and velocity. The acceleration is dependent only on the properties of that planet, right? Okay, with that being said, what else can I expand this question into? Okay, let's do some sketches. Okay, so let's say sketch the what graphs do I want to sketch? Okay, so let's say displacement time graph, velocity time graph, and acceleration time graph. Okay, so I'm sketching all of them, essentially the ones that we know how to sketch for this question, right? Okay, so I'm going to start off with the let's see position in meters versus time in seconds. Okay, and I'm going to take upwards as being positive. Okay, so what does a position time graph look like? Okay, so for this ball, it starts out at 0, okay, and at time 7, it ends back at the guy's hand, or at the alien's hand, and we know at time 3,5, it reaches its maximum height, which we calculated 61.25 meters, right? Okay, so the question is, what does this graph look like? Is it a straight line graph? No, so it's not, right? So it starts out very fast, okay, but the acceleration is acting in the opposite direction, so it slows down, so it plateaus until it reaches a velocity of 0, in which place it's not moving anymore, right? At that point, it starts out slow, and now it's actually, the acceleration is helping it move, so it's speeding up, so we get a stronger gradient. Okay, so once we've done that, let's go on to the velocity time graph. So velocity in meters per second and time in seconds. Okay, so we know the velocity starts out at 35 meters per second, and it ends, remember, it ends because the alien catches it at the point of release, it's going to end with the same velocity. So velocity 2 is going to be 35, but it's going to be downwards instead of upwards, right? And that's because of that rule that we said, that the velocity at any given displacement if these displacements are equal, then the velocities are equal but opposite in direction. So it starts at 35, so it must end at minus 35. It hits a 0. The velocity hits 0 at 3.5 seconds and hits 7 seconds. At 7 seconds, it's minus 35, and we're left with, we have a constant acceleration, so we have a constant velocity, right? And again, this is taking upwards as being positive. So we have a straight line graph going through our 3 points. Okay, and remember, our gradient is equal to our acceleration, which was minus 10. So the fact that we have a minus gradient is good, or a negative gradient is good. Yeah. Okay, and lastly, I'm going to do the acceleration in meters per second squared versus time in seconds. Okay, and our acceleration was constant, and it was a minus 10 meters per second. So for the full 7 seconds, it experienced that acceleration. So that's going to be just a straight line. Okay, so maybe for fun, or for just to test you guys, or test yourselves out, try drawing these graphs with taking the opposite direction as being positive. So try taking this graph and saying, okay, let the downwards direction be positive. Okay, if we had that, let me just do the acceleration one very quickly. So if we take the downwards direction as being positive, then our acceleration becomes positive 10, and it's the same thing for 7 seconds. So we have a straight line like that. Okay, so what happens for the velocity time graph and the displacement time graph? What do those two graphs look like? Maybe do that for yourselves. Okay, cool, guys. So I'm going to end this video here. It's another long one, but I hope it helped you guys. We went through some theory and we did a nice long question. So thanks for watching, guys, and I hope you found this useful, and stay tuned for more.